Hello, welcome to the video of the day. This video is going to discuss the torque due to a magnetic field on a loop which carries current, I. And I forgot to draw my current there. I want my current to go this way. So I have current I flowing around that loop. So we've already talked about the force on a loop of current in a uniform magnetic field, I should say. And we've already said that the net force is zero, but it turns out the net torque doesn't have to be zero. It might be. It just depends on how the things line up. So to keep things really simple, I have drawn a rectangular loop, and I'm basically going to massage this into a certain form and then claim that that form works regardless of the shape of the loop. I'm not going to prove that. I'll leave that up to you. So it's kind of hard to picture this, right? So the idea is I've got a rectangular wire, and it's oriented at different angles, and there's a magnetic field going in the Y direction, and the angle between the normal to the loop, so you think about that loop as if there's like a soap bubble suspended in between them. They're spanning that rectangle, and there's an angle between the magnetic field and the normal to that surface, and we call that angle theta. All right, so let me redraw this from a bird's eye point of view. From the top, well, from the top you can't see the depth. Oh, and I'm labeling the sides A and B, and I'm going to have the top side, the bottom side, the left and right side. So from the top, I have my loop. All you can see is the top wire. Over here is the left, and over here's the right. Here's the normal, and then the magnetic field lines would come in from the left. And the angle theta would be measured with respect to the magnetic field. Okay. All right. And just for completeness, I wrote out the magnetic field would be in the Y direction, if I call that the Y direction. Okay, so from the top, then, we can ask about any possible torques. We know the net force is zero. Let's talk about the net torque. Remember, what's the formula for torque? And remember, the formula for torque is R cross F, where R is the kind of the lever arm, the vector, which just shows how much leverage you have. So now here's the thing. Think about this wire that's on the top. I should label the current on the top wire. The bottom wire would be going backwards, so I won't draw it so we don't get confused. But this vector along the top would have, so I'd have V cross B. It would generate a force on the top wire, which goes out of the board, and on the bottom wire will be into the board, but there's no twist, and they just cancel out. However, on this end, you have current. I'm going to draw a blue dot here. The current is coming out of the board at this point along this line, and over here, the current will be going into the board as it goes up, over, and down, up, over, and down. And on this wire, on the left, think about that. You have B cross B. Over here, you would get a force going that way. And over here, you would have a force going that way. and these two forces are going to cause the loop to twist. So there is a torque. To evaluate it, we're going to need to know the formula for the force, and we need to know the lever arm for each one. But notice if I said that the total length was equal to B, this whole length is B, which means the lever arm would be B over 2 for each of them. Okay, it's going to turn out that they give identical torques. Or sorry, each one separately gives an identical torque that just adds up and doubles up. So we end up with a nice simple formula for this. All right. So I need my eraser. So these are straight wires, and so I need to find the torque from the left plus the torque from the right. I've already argued that the torque coming from the top and bottom segments are, well, there is no torque coming from the top and bottom sections, so it doesn't matter. And that's just going to be, well, I already showed that they work together. So it's going to be I times the length on the left, but the length on the left I called A in that rectangle because the wire had dimensions A and B. I times L times B, and there's going to be a sine theta from the cross product. Similarly, from the right, well, that was the force, and then I need to, because the cross product can get a theta, and I also have the lever arm, which was a B over 2. This is from the wire on the left, and then from the wire on the right, I just get a doubling. They just work together. You can go through it, and you can see that it works out that way. So I'm left with the following expression, and reinstating vector quantities, I see that the torque on the loop is that's going to be A, B times, let's think about that. If you think about it, the sine theta is coming from a cross product between the magnetic field and what vector? Well, it's actually the normal vector. Okay, so that gives us the torque on this loop. And there's a couple caveats, or a couple things I want to say. One is A times B is the area. And furthermore, if you were to wind that loop over and over and over, each one laying parallel to this loop, you're just going to get that same torque in time. So if you have in turns, you would want to multiply by the number of turns. Okay, and we're going to see factors like that a lot with magnetic fields. So get used to it. Okay. So let's think about what happened. We had this loop, and in the presence of a magnetic field, it gets twisted. We've seen something like that. That's what happened to an electric dipole in the presence of an electric field. So in that case, remember, for an electric dipole, we said that the torque equaled the dipole moment vector, electric dipole moment vector, cross E. So I guess you can take that as a motivation. What we want to do is define a new vector quantity, which would be the number of turns times I times the area times the normal to the area. And this is called the magnetic dipole moment. And the formula for the torque on this loop equals mu cross B, the magnetic field. So this is the magnetic dipole moment, whereas up here we had the electric dipole moment. They both can cause things to twist, which means they can cause motion, which means you can think of them in terms of, as you, depending upon the angles, it's all dependent on the angles, but then depending on the angles, there's some potentiality for motion. So just like you can have a torque for electric dipoles and then a torque for magnetic dipoles, their potentiality for motion tells us you can think about a potential energy. In the electric dipole case, potential energy, that was equal to minus P dot E. No surprise then. The potential energy stored in a magnetic dipole is going to be minus mu dot B. So what that means is that if you think about it, what it means is that if you have a loop like this, whose normal points that way, the loop wants to align itself with the magnetic field. And if you were to twist it back, that takes energy. You'd have to do work to go against that torque. There's a potential for, there's a potential energy, because if you let go, it's going to flip back. And so mu starts out this way. If I were to rotate this so that mu and B are opposite each other, the dot product would become negative, but you're actually gaining potential energy, so you need that minus sign in there to get it all to work out correctly. Right, so that's the magnetic dipole moment, and it plays the same role for magnetic dipoles as electric dipole moments did for electric dipoles. One other comment. The formula for mu, remember I derived it with a rectangle, but the formula for mu vector is the number of turns times I times the area times the normal vector, normal unit vector. And even though I used a rectangular area to derive this, the final result is completely general. And so you can deform and bend it, and it's the same shape, same effect. So it's, in the end, the final result is completely general. So, so that is our last video describing the effects of magnetic fields. The next videos are going to turn to how we create magnetic fields, and we're going to learn about them. There basically going to be two main formulas, or two main results that we have. There's a formula called Biot-Savart, and it gives the formula for magnetic fields when the current is steady. We call that magnetostatics, steady currents. And that is analogous, not equal to, but analogous to the way that we use Coulomb's law. Remember, Coulomb's law is only true when the charges are stationary. So the law, or the formula by Biot-Savart, is analogous to the way we use Coulomb's law, but for magnetic fields. And then For other shapes, we're going to use something called Ampere's law. And Ampere's law is different than Gauss's law. In fact, it's actually, it's different than Gauss's law, but Ampere's law, morally speaking, the way we kind of use it to evaluate the magnetic fields coming from highly symmetric configurations is analogous or reminiscent of Gauss's law. So it's not equal to Gauss's law, but we already saw Gauss's law for magnetic fields just says that in any closed surface, the magnetic flux is zero because there are no magnetic monopoles. We just happen to use Ampere's law so in an analogous way. So I kind of think of it as you could do honest work. That's like using Coulomb's law, or it turns out Biot-Savart for magnetic fields, or you can use the slick way using Gauss's law, or for magnetic fields, the slick way is going to be using Ampere's law. After we have that, we will talk about what happens when you start incorporating time dependence. That will lead us to Faraday's law, and then we will get to Maxwell's equations. So that's kind of the roadmap for the next few videos. It'll be a few, more than a few. All right. So hopefully you're following along. Please work through these. Keep up on sapling. Practice. When you do sapling, make sure to work through the derivations too, though. Don't just use the formulas out of the book or online. I mean, the examples are all pretty standard. You can find a formula for all these, but to learn it, you have to work it through and do the calculus, do the integrals. Yeah, it's as much fun as it sounds. I know. Sam's just like, I can tell. She's just beaming right now, thinking about all the integrals we get to do. So it's for you, Sam. All right. See you guys.